Hello, and welcome to Make It Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement for creating these kinds of technical videos in the public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark and the continuous motivation of creating these kinds of technical videos in the public domain. And I would like to thank Almighty for my good health and broad mind. And I would like to thank my friends, followers, my dear students, and subscribers for their continuous support of creating these kinds of technical videos. And today's topic of interest is stress strain diagram of different materials. So here we are going to commemorate the different material stress strain diagram. And first we are going to understand what is the stress strain diagram. What is the important thing in this stress strain diagram that we have to introduce. Here, in the stress strain diagram, Hooke's law is the basic law which holds good up to the proportional limit. Up to the proportional limit, the stress is directly proportional to the strain. So this is called as a Hooke's law, where the Hooke's law will produce the stress is directly proportional to strain. This proportionality constant would be the Young's modulus. Therefore, the Young's modulus is the property. The Young's modulus is the property of the material. Therefore, here the Young's modulus is equal to stress by strain. Therefore, the property of the material can be found out by how much stress we are inducing in the material and how much strain is produced. So, with this, we can calculate the Young's modulus or modulus of elasticity of the material. This Hooke's law holds up to purely up to the proportional limit. The proportional limit, up to the proportional limit, this equation can be satisfied. So this we have to know. There is a finite difference between the proportional limit as well as the elastic point. The proportional limit is bit below the elastic limit in this stress strain diagram, that we have to know. Here we can say, let this is the my elastic limit, where this is my proportional limit. In the proportional limit and elastic limit is divided by a small thing, that is the difference between the strain energy and the resilience. The difference between the strain energy and resilience, if you understand the difference between the strain energy and resilience, we can easily understand the range between the elastic limit as well as the proportional limit. Therefore, the proportional limit is bit below the elastic limit, that you have to understand. So next is the upper yield point and lower yield point. So here we know that the upper yield point is somewhere here, the lower yield point is somewhere here. In the upper yield point, reduction of area is takes place, and lower yield point molecules carrying the load. Here, without producing a stress or without producing a load, a material is deformed. The material is getting deformed. So that is why the curve is giving like this. So, and one important thing. So when you see these kinds of a stress strain diagram, you can easily understand this stress strain diagram is for the elastic materials. Whenever you identify certain points like proportionality, elastic point, plastic point, upper yield point, lower point, ultimate point, breaking point, if you have an idea or an thing to visualize these points, you can definitely say this stress strain diagram is for an elastic material. If you if you seen in a plastic material, it will get like this. It will be, the stress strain diagram will be like this. What it means, whenever the elastic material or ductile material will show a definite evidence. This you have to know, definite evidence before breaking. Whereas in the brittle material or a plastic material, it won't give certain evidence before breaking. So this is our understanding about the stress strain diagram. And moreover, we have to remember the resilience, modulus of resilience, proof resilience, and strain energy. These are all come when the material is stressed up to the elastic. This one is different, up to elastic limit. This is up to proportional limit. So these three will come up to the proportional limit, whereas the strain energy will come up to the elastic limit. So this we have to understand. Okay, and the last one, if the material is strained, so under the stress strain diagram, this thing is called as an work done on the material. So this is called work done on the material. Therefore, up to the fracture point, which is called as a toughness or modulus of toughness. This is modulus of toughness and toughness. These two things come up to the failure, up to the failure point. This you have to understand in this sustain diagram. Okay, so here I would like to give some glimpse in the sustain diagram. Here the permanent set is there. Permanent set is without any addition of load, deformation occurs. This permanent set is nothing but your upper yield point and the lower yield point. And the ultimate point, the molecules are breaked. Therefore, necking is formed. When the necking is formed in the ductile material at the ultimate point, the necking is nothing but a reduction in area, the point at which maximum load can be withstand. And next one is the breaking point. In the breaking point, failure occurs. The breaking point, failure occurs. And next we are going to discuss those resilience, toughness, and modulus of resilience and modulus of toughness. The resilience is the strain energy up to the elastic limit, so it is called as a resilience. Toughness is the strain energy up to the fracture point, and the modulus of resilience is the strain energy stored per unit volume up to elastic limit. And modulus of toughness is the strain energy stored per unit volume up to the fracture point. So these are all some definitions which you have to understand and you have to know in the stress strain diagram. Next is the Hooke's law. In the Hooke's law, the stress is directly proportional to strain. It is up to the proportional limit, and for the mild steel will be having a better evidence. It is the mild steel is a more ductile material than anything other, because the mild steel is the medium carbon steel or low carbon steel. It have very good elastic property. Because of this, it produce more Young's modulus. We know that the Young's modulus of the mild steel is 210 gigapascal. Therefore, this is maximum. And diamond will have 2500 gigapascal, but we are not at all considering the diamond for stress strain diagram. We cannot produce diamond, we cannot induce the diamond in the stress strain diagram. That is why we are not at all considering the diamond's Young's modulus, where the metals like mild steel will have a high Young's modulus than any other material. Okay, here you have to understand a thing called permanent deformation. This permanent deformation, that is the stress, permanent deformation stress is equal to k into e power n. The condition for necking is the permanent deformation. The condition for the necking is d sigma divided by d E, that is difference in stress divided by difference in strain, which is equal to stress in necking, that is equal to N, that is equal to E of T, where K is the strength coefficient, and n is the work hardening. We know that the normal engineering stress or nominal stress, which is the formula we are having, the stress is equal to load by area, that is a resisting load by area, where true stress is the instantaneous load to the instantaneous area. We have to understand one thing in the stress strain diagram, where in the ultimate point, as the definition said, and the ultimate point, the necking will start. Therefore there is, in theory, we are producing the ultimate to breaking like in the downward direction, that we are assuming have the uniform area is there in the material. But in the practical case, the necking is formed at the ultimate point. Therefore reduction in area is there. Therefore the true stress strain diagram is being tend to upward, and it will produce breaking at upward breaking. So this region is called as true stress and true strain region, where we are calculating the instantaneous stress to the instantaneous area, or instantaneous load to the instantaneous area. So that is called true stress. True stress is nothing but the ratio of instantaneous load to the instantaneous area. And we know that true strain is lesser than the engineering strain, whereas true stress is more than the engineering stress, where we can easily found the formula of true stress and true strain, where true stress is equal to sigma e. Sigma e means engineering stress, so engineering stress into 1 minus strain, engineering strain, 1 plus engineering strain, where true strain is the ln of 1 plus engineering strain. With this formula we can found the true stress and true strain value of the material. Now we are going to discuss some of the stress strain diagram of different materials. First, for the perfectly rigid material, there is no strain, therefore stress we can build up. The material will not deform all under the action of load. That is called perfectly rigid material. We know that rigid material won't deform. Therefore, in the y-axis itself, it will have a stress. Next is the rigid body with strain hardening. The rigid body with strain hardening, after a certain point, it will produce some of the strain values. The rigid up to the yield point and strain hardening, and the deform, that is deform plastically up to the rigid up to the elastic point. So sorry, this is the yield point. Up to the yield point, the material will become rigid. After that, after the yield point, and strain hardening will be done. Strain hardening may be linear, may be non-linear, it is according to the material. Next is the cementite carbide or plaster of Paris. So, cementite carbide or plaster of Paris is always produced linear, where the ideal plastic up to the yield point there is no deformation. After that, there is no stress, only deformation is happen. Whereas elastic and strain hardening, it is bit linear, it show some evidence in the yield point. And next, for the rubber is a parabolic in nature, where the perfect elastic is linear in nature. Everywhere there it will understand the Hooke's law. Everywhere you can get the Hooke's law. In the compression, the perfect elastic in compression also, it will produce a beautiful curve. It will produce a super evidence in before fracture. Next is the cast iron material. Cast iron is the, we know that it is a brittle material. The normal stress in here normal stress is in 90-degree plane. Therefore, no evidence before breaking. For brittle material, you have to understand that the yield point as well as the ultimate point and breaking point more or come, it's very closer at the end. Therefore, it won't show any evidence before fracture. Next is the elastic and perfect plastic. It is linear up to the yield point. After that, it is a perfect plastic. Therefore, no stress, only strain is there. And now we are going to consolidate certain materials which we are using in day-to-day application. That's stress strain diagram we are going to compare in a single graph. First, we are going to take concrete, cast iron, and mild steel. Here, we know that mild steel is the perfect elastic and a ductile material. Therefore, it shows the evidence before fracture. That is, the smooth and irregular curves are there. Therefore, it will give the evidence before breaking. Whereas the cast iron and concrete, it won't give any evidence before breaking. And here we can know that the, the tensile strength of the concrete and cast iron is compared. The cast iron is bit better than the concrete. That is why in the reinforcement concrete, the MS, the heat treated MS bar is put into the concrete for making better tensile strength. Therefore, by making the composite, it will produce better tensile as well as the compressive strengths. Next, we are going to compare brass, copper, aluminum alloy, and annealed copper. So, we know that all are the non-ferrous material, but it will produce better elastic in nature that we have understand earlier. But in the stress strain diagram, it also produces there is no evidence before breaking. What it mean? We are thinking it is a ductile material, but it is not a ductile material. It is bit like a brittle material because it does not shows any evidence before fracture. When we elongate, it can elongate like an elastic material, but at a certain point, it tend to break. You can easily visualize the cast iron is mentioned here. There is no difference between the cast iron as well as the copper or aluminum or annealed copper or a brass. But a graph is slightly more or less, but the graph will not show any evidence before fracture. So this is our understanding about non-ferrous materials too. I hope with this I have given an enough knowledge and enough content in this sustain diagram of the different material. So with this I am going to close the session today. Thank you. Thank you all.